Hi gentlemen, today we'll be discussing empirical versus molecular formulas. Here we're basically just discussing the difference of the lowest whole ratio of a formula versus the actual formula. So we're only going to do this when we discuss covalent compounds, because ionic compounds are always the reduced version. For example, if I had Na2Cl2, we always reduce that to NaCl in the case of an ionic compound, when we have a metal and a nonmetal. When we're dealing with just nonmetals in covalent compounds, we can reduce to an empirical formula, which is the ratio of whole numbers, but really what we want is the molecular formula. Okay, so you can see here an empirical formula. An example would be CH2. We've taken the molecular formula of C2H4 and reduced everything, right? We've divided everything by 2 to the lowest whole ratio of CH2. So that's your difference between a molecular formula and an empirical formula. And you'll see why in a minute, why it's important to understand what both are. Because we will deal with empirical formulas to help us determine molecular formulas in a minute. Okay, so just a little bit more here. Methanol is a compound. Okay, in this case, its empirical formula is CH2O. Its molecular formula happens to be the same. And so that's what you see here when we talk about methanol. Ethanoic acid, on the other hand, has the same empirical formula, but has a different molecular formula. And this is where you see the importance of empirical versus molecular when we talk about covalent compounds. Again, in ionic compounds, we're talking about that crystal lattice. We could have an infinite number. It's that lowest whole ratio in an ionic compound that matters. But again, in covalent compounds, there's a very big difference between ethanoic acid and methanol. Even though they have the same empirical formula, the molecular formulas are different, and that's important to understand. And we'll see how to calculate the two versions here, in a minute. Okay, so in order to calculate the empirical formula of a compound, you need two pieces of information. First, you need to know what elements make up that compound and the percent composition of each of those elements. So we've just learned how to calculate percent composition. So now we're going to use that to help us calculate the empirical formula, or that lowest whole ratio involved. Okay, so the important thing here is, because we're using percentages, and rather than trying to convert to certain numbers of grams, we're just going to assume that we have a 100-gram sample. And then what we can do is we can actually convert our percentages to grams straight away. Okay? And then we're going to use the molecular mass of each element to determine sort of that ratio of each one, then divide each element by the smallest amount, and use the ratios calculated to find the empirical formula. So let me show you what I mean. Okay, so we have an unknown compound. We know that it has 40% sulfur. So we have a percentage of sulfur is 40.1%. We know the percentage of oxygen is 59.9%. So if we have 100 grams, we can just take these percentages and convert them to grams. Okay, because we have 100%, we have 100 grams. 40% of 100 grams is 40 grams. Okay. So now all we need to do is find out the molecular mass of each of these elements, and then calculate the number of moles. So we'll do. So if you remember, we have this formula, N equals mass over molar mass. So we go to my periodic table, find sulfur has 32.06. Okay, so I can plug that in for M. And I will see that oxygen has a molar mass of 15.999. We'll round that to 16 grams per mole. And so now we just need to calculate. Okay. So we'll take our 40.1, divide by 32.06, and I made a mistake. We'll go 40.1 divided by 32.06. 32.06. We get 1.25, and that's moles. Okay. And then we're going to do the same thing with our 59.9 divided by 16 with 3.74. Now to get the ratio of these, we're just going to divide by the lowest number of moles available. So the lowest number of moles is 1.25, so we're going to divide everything by that lowest mole number. So obviously here you have 1 sulfur, and here you're going to have 3 oxygens. Okay, if it's close, 2.99, we can round up to 3. So now we can see our formula is sulfur with 1 and 3 oxygens. So our empirical formula must be SO3. So now you can see here we have an empirical formula, but we don't know the actual molecular formula. This is the basic lowest ratio, but we're not sure if this is the actual molecular formula. And this is an important piece of information, because if you can see the difference here, you look at acetylene has an empirical formula of CH. Benzene also has an empirical formula of CH. However, their molecular formulas are very different. Acetylene is C2H2, and benzene is C6H6. Acetylene is a gas at room temperature, while benzene is a liquid. Benzene has a strong odor. Acetylene, on the other hand, is odorless. And if you're looking at acetylene, you're looking to burn something, you'd want acetylene, whereas benzene, on the other hand, is very poisonous and carcinogenic. So it's important to know what you're dealing with. And so to do that, we need to know the actual molecular formula, we need to know the we need to know the molar mass, the total molar mass of the unknown compound to determine it. So if we look, for example, at a compound with an empirical formula of SCl. That tells us we have 1 sulfur and 1 chlorine. Okay, so now we need to determine the molar mass, the molecular formula. We also know, though, we have a molar mass of 135 grams per mole. So if we determine the molar mass of the empirical formula, so if 1 sulfur atom is equal to our 32.06, and chlorine has a 35.45 molar mass, we can add these up and determine the molar mass of the empirical formula. So we have a 57.51 grams per mole molar mass of the empirical formula. So all we need to do now is take the molar mass of the actual molecular formula and divide it by the molar mass of the empirical formula. And this ratio will tell us how much we need to multiply this overall ratio to find our molecular formula. So I'm going to take 135 and divide it by 57.51. And that gives us a number of 2.35. Now, you can see here this gives me a 2.35 number. And I can look at this and say, this is going to give me S 2.35, CL 2.35. And that doesn't really make sense. So I can see now that I've made a mistake. I need to go back and look at what I've done. And I can see very quickly that by adding these up, I added 3 plus 3 and gave me 5. So this should be 67. Right? And this should be the answer to my problem. Okay? So these are types of things you need to be looking for. You should be getting a whole number as your final answer. So be careful when all these calculations. So now I get 1.999. This is close enough. We can round something like that to 2. So now I need to know that I need to multiply this ratio by SCl, which gives me S2Cl2. Okay, so before you go on, to answer this question now, what I want you to do, as to show that you've done this and figured this out, I want you to try question A here in the problem set. Okay, put your answer into the Verso question. Okay, this will cover calculating an empirical formula and calculating a molecular formula. Okay, so be careful, look for those mistakes, make sure you have whole ratios, double check your math if you have to.